class labels, which was a lot more than the 20 labels we used in the cityscape dataset. The style of the generated image is controllable. You can steal styles from the style image, and it achieves all this using a fewer number of parameters. So how did we do this? Here's our motivation. A standard deep network consists of convolution followed by normalization. We know that normalization yields nice properties such as smoother gradient flow or maybe invariance to input scaling, but we found that doing so with input semantic map gives sometimes too much invariance, sometimes even losing semantic information. So here's a little thought experiment we can do. Let's say the input semantic map was just flat uniform label, for example 100% grass. Then after convolution, we're going to get activation, and at each channel, we're going to have uniform neural response at each channel. Then after normalization, because we subtract the activations by the mean of the activations, we're just going to get 0. And this is true no matter what kind of class label we're going to use. And this was indeed true in case of Pixelpix HD. If we input flat label, no matter which class label we use, we always end up with just a gray image, which just means 0 everywhere. So here's our solution. We propose to actually just provide this semantic information after every normalization. And this is indeed kind of what we did. And as a result, using our model, you can see that even if we input a uniform flat label, we are going to get the correct texture for each class label. So this is what we did. We extended the idea of batch normalization. I think you probably all know that batch norm consists of two parts. First is the normalization parts that computes the mean and variance and make the output distribution zero-centered and unit variance. And the second part is the learned affine transformation part that allows more flexibility to batch normalization. And we call this part denormalization because after the second part, the distribution is not normalized anymore. And the key to our approach is we made this denormalization part conditioned on the semantic map. So in more detail, given semantic map, we pass it through a couple of convolutional layers to produce tensors of gamma and beta, which are going to be the parameters of our affine transformation. Then given the normalized statistics, we do element-wise multiplication addition. It's basically applying gamma and beta to the normalized statistics. It's closely related to many previous works. One of them is class conditional batch normalization, which was actively used in image generation on ImageNet dataset using GAN, including spectral normalization GAN, self-attention GAN, and also big GAN. Here, the affine parameters, affine transform parameters, are conditioned on the one-hot class vector. But in this case, it's class conditional, so you basically have the same class vector for all pixels of the generated image. So the affine transformation parameters are actually spatially uniform. Conditional normalization can also be used in adaptive instance normalization for fast style transfer. What you do in this case is if you just replace the affine parameters by the ones produced by the style image, then you basically get the output image rendered in the style of the style image. Our method is also closely related to the spatial feature transform last year in CVPR. It uses conditional normalization for the task of super resolution, but in this case, the affine transformation parameters are conditioned on the predicted class label of each pixel. So here we are, we have the spade module. It's designed to replace the batch normalization of any deep network. So for example, the residual block we're going to have now will look like this. So So instead of batch-norm, ReLU, convolution, we are going to have spade, ReLU, and convolution. And at each spade module, we're going to have the input semantic map as its own input to its layer. Then now we can use the same architecture that's used in many popular GAN generator architecture, which was residual ResNet-based architecture. So you start from random noise, and then you gradually upsample the image, but at each ResNet block, we're going to feed in the semantic map to provide the semantic information. And this differs from the architecture of Pix2Pix HD, which was state-of-the-art previously, which has encoder part that processes the input semantic map and decoder part that produces a photorealistic image. Now, in terms of this architecture, we have only the decoder part of Pix2Pix HD, and this saves a number of parameters of the generator architecture. We also have GAN loss, like Pix2Pix HD, to enhance the visual realism of the output image. We also have other tricks that we use, and it confirms the findings of other GAN papers. For example, we use a larger batch size, and we confirm that it actually helps the output quality of the generated images. We go from 8 in Pix2Pix HD to 32 in our case. We also used synchronized batch normalization, which synchronized the statistics of each GPU. We also used spectral normalization with hinge loss, and it helped our training in terms of both the stability and also the final output quality. So here are the results. Given this input semantic map, this is the result of CRN and Pix2Pix HD. I think Pix2Pix HD creates these artifacts because we have large flat label. And ours generate the correct texture even for the background. You can see that Coco Stuff dataset is more diverse. It contains animals, people playing sports, and interior, and food pictures, and so on. And this is the results on the outdoor subset of 8020K. Now that we sufficiently reduced the size of the dataset, we can actually compare with the result of semi-parametric image synthesis. And you can see that on the top left, the result of SIMS looks very realistic because it steals the real image patches from the training set. But once you compare it with the input semantic map, you can see that it's actually not perfectly observing or respecting the input semantic mask. Here are some more results. This is indoor. And this is the result of Cityscapes. And I think at this point, Cityscapes dataset is simple, that pretty much all methods kind of saturated and all results look pretty good. So here are some evaluations. We first did user study. We asked to mechanical Turkers the following question: which image looks better as a realization of this segmentation mask? And then we showed side by side our result and the competing result. And we counted how many times our result was selected as opposed to the competing result. So 50% would mean that, you know, those two images look pretty much the same. And if we get 100%, it means the users always selected our method. And you can see that our method consistently gets over 50% chance, over 50%. And you can see that on Cityscapes dataset, because the dataset has kind of saturated, we're close to 50%. There is a way of doing automating this evaluation process. One of them is called the semantic segmentation score. What we do is, given this output, given the output images, we pass it through pre-trained semantic segmentation network. We get the predicted semantic segmentation, and we compare it with the original semantic segmentation. And the intuition is that if our generated images look realistic, the predicted semantic segmentation should agree with the original semantic segmentation. And you can see that our method performs better than the previous method. And interestingly, our method actually gets higher score than using the ground truth image. And I think this is because when humans label the ground truth image, the semantic segmentation is not perfect. While in our case, we start from the human label semantic segmentation, so we have perfect information about the semantic segmentation. We also used FID, which computes the mean and variance of feature activations of the generated image using pre-trained image classification network. And we compare this mean and variance against the mean and variance of the ground truth images. And red line is the result of comparing it against the ground truth training set. And you can see that ours is close to the ground truth FID. And you can see that since the semi-parametric image synthesis method also achieves pretty good result. And it's because it actually steals the real patches from the ground truth training set. So here are some pros and cons of different evaluation methods. I think the user study is the ultimate metric that we want to optimize for. We want to generate images that look the best to human eyes. However, this human study is not automated. It's also not so reproducible, and it's known to be pretty much sensitive to the question asked. There are two other automated evaluation metrics we used. One of them was the semantic segmentation score. But the thing is, I think this evaluation metric has already saturated, as you can see in the graph, comparing with the ground truth result. And it's also dependent on the pre-trained segmentation model. Lastly, we have FID. It's automated, but the drawback of this method is it actually doesn't evaluate the correspondence to the original semantic segmentation score, semantic segmentation. So even if it ignores semantic segmentation map and just generate any random realistic image, it's still going to get a very good FID score. We also have nice separation of semantic and style control. So we know that changing the semantic map will allow us to change the semantics of the generated image. Changing the style changing the random vector in the latent space will allow us to change the style of the generated image. But we found that naively doing this will not result in generating different style of the image. So we actually used an image encoder and trained it in VAE style to make the generator network actually respect the latent vector. So what we do is we feed in the ground truth photograph and we pass it through image encoder to capture the style of the photograph into a latent vector. And then we trained it in VAE style using KL divergence loss. In the end, we got this demo tool that can allow us to change the style of the image. So we have multimodal results on Flickr dataset. So given this semantic map, just sampling different random vector in the latent space allows us to generate different stylization of the output image. So we have more results on Flickr. The way we trained this dataset on Flickr is we actually just downloaded lots of images on Flickr and we passed them through a pre-trained semantic segmentation network, and we treated this predicted semantic segmentation as the ground truth semantic map. And then we created this data set and then trained the inverse direction. Thank you for listening. I'll be happy to answer questions.
So we used the reconstruction loss, basically. Did this hurt the realism of the output? No. Will this hurt the realism of the output?
Wait, does it matter the realism now?
It hurt the realism.
Oh. So the question was, when I train the model using VAE style, using the reconstruction loss, does it actually hurt the final output quality? My answer is no, because once we use this VAE loss, it tends to produce more vibrant images. I think without the VAE loss, it just generates the most stereotypical image, and it kind of sometimes looks boring to human eyes. But using VAE loss, it becomes a little bit different. It becomes more, the output becomes more diverse, but it actually looks better to human eyes sometimes. Any other questions?
Let's thank the speaker.